So for this I'm going to talk about integration of rate laws. So we begin by starting for the first order reaction. First order reaction. So a simple first order reaction would be of A goes to products. Now, we know that if it's first order, then the rates R would be K A to the first order. The rates would also equal minus 1 over A minus 1 over A d concentration A over dt. Now, by definition, I could define K subscript A equals A to the K. Now, if I move this A over here, I would have AK concentration A equals D concentration A over dt minus. This now becomes Ka concentration A. Now, if I multiply dt on both sides, I will have minus dt on both sides, and bring this on this side, I would have 1 over concentration A d concentration A equals minus Ka dt. Now, we could move this to this side and we would have minus 1 over A d concentration A plus Ka dt equal 0, or d constant C, where C is integration constant. dC is 0. Now, this is a separable differential equation, and we could separate this easily. If we say the integration constant is 0, then this becomes 1 over A d concentration A equals minus Ka dt. Now, if I integrate this from 1 to 2, integrate this from 1 to 2, I would have ln concentration A 1 to 2 equals minus Ka T 1 to 2. Now, this would give you ln A 2 over A1 equals minus Ka T2 minus T1. Now I could say T1 equals 0 seconds, and then I could call A1 AO and A2 at A of T. This becomes ln A of T over AO equals minus Ka T, giving that T2 equals T. Now, if we could, this equation is correct, but there is an easier form. The easier form could be ln AT minus ln AO equals minus KAT. If I move this to this side, I have ln AT equals minus KAT plus ln AO. This resembles the equation y equals mx plus b. This is the y-intercept when x is 0. This is the slope is minus Ka. So a graph of x, in this case which is t, faces ln concentration A at t. Well, you can't, because this has a unit molarity, you would have to divide it by a standard concentration. Because when you plug in ln in a calculator, you can't plug in ln to molarity. So you have to divide it by a standard value to cancel out the units. However, the slope would be negative, as you can see here. The slope m will be minus Ka. The y-intercept would be b. Back to this form. With this form, you could e both sides. If you e both sides, you end up with A T equals AO and E minus KAT. Now, let's go back to this. This is the general equation that gives you the concentration of a species A at a certain time. Now, let's say that we want to find the half-life. Let's get back to this equation. Now, we know that when T equals half the time of the reaction, this concentration would equal half of AO, or 50% of AO. Now, this doesn't only work for half-life. You could do it for when T equals 30% of the concentration. Then it will become AT equals 30% AO, or 70%, whichever way works for you. But the general way is half-life that we're looking for, half the concentration. So we substitute A of T for half of AO, becomes half AO equals AL E minus KAT. This cancels off. You're left with half equals E minus KAT. Now, let's talk about the function ln of x. Now, ln x is greater than 0. When x is greater than 0 and less than 1, ln of x is negative. Elsewhere, ln is positive. So, back to this equation, if I ln both sides, I'll have ln half equals, the e cancels out, which should give you minus Ka T half. We'll call this half, because we're dealing with half. ln half, as I said here, would be a negative value, which would give you negative 0.693 equals minus Ka T half. Now the negatives cancels out. T half-life would give you, for first order, 93 over Ka. Perfect. Now, what about the units of k? Let's find the units of the rate constant k. Units of rate constants k in the first order. So we know that r equals k a first order, and we know that r equals minus 1 over a d concentration a over dt. A has no units. A is the coefficients. Concentration of A is moles over liters, which is molarity. So the units of this would be molarity over seconds. Hence, you can write ms minus 1. So the units of rate is ms minus 1. So K becomes R over concentration of A. The rate becomes ms minus 1 over concentration of A, which is m. So m and m cancels out. So the units of K becomes s minus 1. Now, what about in general? Can we find the rate constant in general? I think we could. If we say the rate equals K for, well, it depends on the order. It could be a first order, it could be a second order, a third order, which is actually rare. But let's say we have a second order reaction and we wanted to find the units for K. The units for K. We could say this equals A. Let's say equals, it depends on A and B. And we call it for M and N. Now, this is for a reaction that deals with, let's do it on a different piece of paper. So this is for a reaction with R equals, where concentration A plus B gives you products. Now, what I'm saying is that, let's say R equals K, A, and B, where M and N are experimentally determined. Our goal is to find units of K. So K becomes R over concentration A to the M, concentration B to the N. The units for R is what? Molarity seconds. Units for this becomes molarity M. Units for this becomes molarity N. This becomes molarity over, this is 1 over molarity M plus N S. Then this becomes K equals molarity. From here, it becomes 1 minus M plus N S minus 1. This becomes K equals M1 minus M minus N. So for reaction A plus B or A plus A, we could find the K value. If let's say N was 0. If N is 0 and S, I forgot S minus 1, sorry. If N was 0 and M, if N was 0 and M was 0, we'll have M to the 1, and which will give you, so let's try it out. If M equals 0 equals N, K would give you M1 minus 0 S minus 1, which will give you M over S. So then the total order of the reaction would be lambda equals M plus N, which is 0. What about if M equals 1 and N equals 1? Then K would be M 1 minus 1 minus 1 S minus 1, which would give you M 1 minus 2 S minus 1, which is M minus 1 S minus 1. which will give you K M minus 1 S minus 1. And then the overall order would be M plus N, which will give you second order. Okay.